Alright, in this video, I'm going to cover section 16.3, which is about fundamental theorem of line integral. And this section is a little bit more theoretical than computational, but it's a bit short section, so I'm going to spend only one video on this. First, let's recall the line integral of a vector field. So let's remember, given a vector field, f, and a curve C parameterized by some of t with a t is between a and b. Then you may assume that either f is on R3 or R2, and accordingly you may assume of t is in xy plane or xyz space. It doesn't matter. And then in the previous section, we learned the line integral of the vector field over the curve C, and more concretely, this is computed as a b f of r of t dot the derivative of t dt. And then this is a vector, and this is also a vector, and if you take the dot product, you get a scalar. So this is just a function of t, and then you just integrate from a to b. So that's a way to compute the line integral. Then now, here's the theorem. The main theorem in this section, namely fundamental theorem of line integral. Which says the following. First of all, as a special case of vector field, we know what's called a gradient field. And now, if our vector field f is written as a gradient of some function, so let's suppose that big F is of the form gradient of some scalar valued function f. So this is a very special kind of vector field. But in this case, the line integral of the vector field, let me just write this way, vector field is written as the difference of the two endpoints of f, the value of f. Namely, this is the starting point and this is the ending point. So pictorially, here's a curve, t is equal to a, and t is equal to b. The curve goes like this. And then if you line integrate in this way over this curve, usually you have to use this formula, but as a special case, if your vector field is given in this way, delta, nabla f, meaning that a gradient of f, and then it's written in this simple form, and this is called a fundamental theorem line integral. And then indeed, you must have seen a fundamental theorem calculus in calculus 1. What was this? Fundamental theorem of calculus. Well, this was like this, right? Suppose you have an integral of some function, but integrand happens to be the derivative of some function like this, and then in this case, the integral is obtained as a difference. Or rather, in the case of single variable, this is the way to compute a integral, right? So you are given some function and find its antiderivative, namely the function whose derivative is the integrand, and then you take the difference between those. And then in the case of a single variable, in principle, you could always find antiderivative. Okay, but sort of like antiderivative for vector field is gradient of f. But it turns out that not every, unlike the case of single variable, not every vector field has an antiderivative, namely not every vector field is written as a gradient of f, but I'll get to this a little later. But for now, let's just work out one example by using fundamental theorem line integral. So let f, or f of xy, be x e to the power of y. Okay, then, and let C be the curve, which is like half of the circle with radius 1. Okay, and then the question is compute, evaluate gradient of f dot dr over c, namely over this curve. And if you want to just compute this directly from the definition, first you compute the gradient, so from the definition. The definition of line integral. What you have to do is to first you compute the gradient, and that is, remember, you take the derivative with x, you get this, and derivative with y, you get x e to the power of y. And then you have to parameterize the curve. In this case, it's a half circle, so it's a with radius 1, so by using the polar coordinates, this, and t is from 0 to pi. Okay, and then so therefore this line integral is written as 0 to pi, and then gradient of f, and then you stick in the parameterization and take the dot product. Okay, it's a little mess indeed. And if you work this out, what is this? This one is, you just plug in the parameterization to the vector field you integrate. So in this case, it's written as something crazy. E to the power of sine t and cosine t e to the power of sine t. Okay, so that's this. And then dot the derivative of r of t. That's negative sine t and then cosine t dt. All right. Here and here. So here is here. All right. And then you work this out, and then you compute a the dot product. dt. And then in principle, you have to work this out, but in practice, it doesn't seem to be a good idea. But in principle, you could do that. So this is by using the definition of the line integral. Okay, but it's not a good idea. Then now, but for this problem, we could use a fundamental theorem theorem. So here, by the fundamental theorem, what is this? Well, we can just plug in two endpoints to f and then take the difference. So in this case, f of r of 0, I'm sorry, r of pi minus f of r of 0. But what is this? Well, this is r of pi is the endpoint. So endpoint is after all 0, negative 1 in terms of x and y. So it's 0, negative 1. I'm sorry, negative 1, 0, sorry. Negative 1, 0. And then r of 0 is nothing but the starting point. So in this case, 1, 0. So all I have to do is just compute this difference. And then the given function f of xy is x e to the power of y. So this is minus 1 e to the power of 0 minus 1 times e to the power of 0, and that's negative 2. That's the answer. Okay. So this is a way to compute this line integral by using fundamental theorem of line integral. Okay, so that means, like I said, it is good to know if a given vector field is of this form gradient of f. But like I said, this is not always the case. It is not always the case that you can find little f so that the big F is delta f. So such a vector field is, in a way, it's a very special vector field. So it has its own name. If your vector field f is of the form gradient of f, then f is called a conservative Okay, then, as a sort of theorem which follows from the fundamental theorem of line integral is this. If f is conservative, then if you have two line integrals of the same vector field over two different curves sharing the endpoints. So we have two endpoints, and we have curve 1 and curve 2. So this one, the curve on the left is C1, the curve on the right is C2. And then at t is equal to a, starting point, you are here, and the end point is here. So suppose you have two different curves sharing the two endpoints. In this case, those two line integrals are equal because that's what the fundamental theorem says. If you have a vector field which is conservative, meaning that f is of the form gradient of f, then the value of the integral is determined by only the endpoints, f values of the endpoints. So therefore, it's independent of the curve. It's independent of how the curve looks like. It is totally irrelevant in between the two endpoints. What matters is only the endpoints. So that means we have this equality. So here, where C1 and C2 share the endpoints. Okay, but in general, let me emphasize this. If f is not conservative, then usually those two integrals are different. It could be the same, but if those two happen to be equal for two different paths, two different curves, that means that's just a coincidence. So usually, if you choose different paths, you get different integral. Okay, so that means another thing we could say from the fundamental theorem is this: if f is conservative, and C is closed, and our curve C is closed. What does that mean? Closed means you come back to the same place, namely, you start from t is equal to a, and then you go around somewhere and you come back to the same point at t is equal to b. It's like a circle. It's called closed curve. So if the curve is closed, namely, more mathematically, more symbolically, R of A is R of B. You come back. And then, in this case, as long as f is conservative, if you compute the vector field over C, you must get 0, right? Because you come back, and so that means in this formula, where is it? In this formula, those two are equal. So therefore, if you subtract one from the other, you get 0. They get cancelled out. They get 0. But once again, this happens only when f is conservative. If f is not conservative, of course, even if you compute the line integral over a closed path, this might be 0, might not be 0. Okay, then now, so that means it is good to know what kind of vector field is conservative. And then let me just note, remember, line integral is physically, it's a work done on a point moving on the force field, so to speak. For example, if your xy plane is the surface of the swimming pool, and then if you like dip your finger on the surface of the swimming pool, and the water is flowing, and if you move around your finger like this, you come back, for example, and then water acts on your finger while you move your finger around, in this case, a circle like this, and then the total work down your finger is the line integral. So that means, for example, let's think about this vector field. Suppose you have a vector field xy, and then suppose xy plane is the surface of a swimming pool, and the water is like rotating around the swimming pool like this. Suppose you think about this situation. Water is rotating like a vortex. Like this. So this is an example of vector field. So in this case, if you dip your finger, let's say here, and then move around the swimming pool, and then you come back to here, and then all this, throughout this procedure, throughout this circling, force is acting for you, right, in the same direction as your finger on your movement, same direction as the movement of your finger. So that means the force is always positive in your direction. So that means even if you come back, the total amount of work can never be 0, right? So this vector field is not conservative. It's not conservative. On the other hand, if you have a vector field like this one, moving in one direction, just water is flowing horizontally like this with the same speed, let's say. If you have a vector field like this, then what if you do the same thing? Namely, you dip your finger somewhere in a swimming pool, on the surface of the swimming pool. Let's say you dip your finger like this, and you move around, and you come back. Then, when you are moving this way, water is acting against you, water is flowing against you. But if you come back, the water is for you, right? The same direction as your movement. So that means it's likely that when you come back, the total force, total work down your finger gets cancelled out against the water and for the water. So that means most likely this kind of vector field is conservative, most likely. Most likely conservative. Okay, so this is not really like a rigorous way of telling if a vector field is conservative or not, of course. So you want to know more mathematical way of finding out if a given vector field is conservative or not. And here's a nice theorem to tell if a given vector field on R2 is conservative or not. A vector field f of xy on R2. So that means we have x component, that's p of xy, and the y component, that's q of xy. This is on R2. And this is conservative if and only if, here's a formula, partial p partial y is partial q partial x. Okay, namely you differentiate x component with y, and you differentiate y component with x. And if they are equal, and then the vector field is always conservative. So for example, here's an example. Let f of xy is 3 plus 2xy I plus x squared minus 3y squared a at j. I use ij notation. You have to get used to both notations. Now the question is f conservative? If so, find the little f, namely its antiderivative, little f, or f of x, y to be precise, so that this given vector field f is the gradient of this little f. Okay, so that's the question. Well, how are we going to do this? So here's the answer. So our p, or p of xy, is 3 plus 2xy, and q is x squared minus 3y squared. Okay. So therefore from this, you compute this partial p partial y. Remember, you differentiate x component with y. And in this case, you get 2x. Then now you differentiate y component with x. And then, in this case, wait a second. Okay, I miscopied this. This is 2. This is 2. And then in this case, you get 2x. All right, so therefore, those are equal. Partial p partial y is partial q partial x. So this implies that f is conservative. Right. So is f conservative? The answer is yes. Now, if so, let's find little f, namely, so to speak, the antiderivative of big F. So let's find little f of x such that gradient is f. Well, so gradient of f is what? Well, x component is a partial derivative of little f with respect to x. And then the second partial derivative, or the second component is a partial derivative of y. And then we want to find the little f such that this is equal to the given vector field. That's a given vector field. So that means x component is 2xy and y component is squared. Okay, so from this, we obtain those two equalities. Partial derivative of f with respect to x is 3 plus 2xy. And f sub y, partial f partial y, is the y component here. Okay, then now what? Well, let's look at the first one of those. So this means the function f we are looking for has the property that if you differentiate with x, you get 3 plus 2xy. So that means in order to recover f, what you have to do is integrate this, but integrate with respect to x. So this means 3x plus x squared y. Okay, it looks okay, but it's not okay actually. When you integrate, don't forget to add c, right? But what's c? Namely the constant of integration. But what's c in this case? Well, c is actually a function of y, because we are treating y as a constant. So here we could put any function of y as long as it doesn't contain any x. So this is equal to this for some g of y. Okay, so therefore, then now we have to determine this g of y, like how? Well, actually by using this. So that means from this, then if you differentiate this f we just obtained with respect to y, then this is 0 plus x squared plus, then now you have to differentiate this with y, and that's the derivative of g with respect to y, so just g prime. Then we want this to be equal to this, y squared. And then what? Well, from this, you will see that you can just solve it for g prime of y, and that is equal to negative 3y squared, because you can cancel x squared. Okay. So therefore, from this, you can recover g of y by simply integrating with y. But in this case, the variable is only y, so you just integrate this with y in the usual way. So that is negative y cubed. But don't forget to add c. But let me use k instead of c for the constant of integration for k constant. Okay, so therefore, the final answer is you just plug this into here. F or f of xy, to be precise, is equal to 3x plus x squared y minus y cubed plus k. Okay, so that's the final answer. So in this way, you can find a, so to speak, the antiderivative of a conservative vector field. But now, let me just mention one theoretical issue about this theorem, namely this theorem, actually. Where did it go? Here's it. This theorem. Strictly speaking, this doesn't work all the time. But it's not super important for this course. But just as a side remark, let me mention this. So the above theorem, the theorem I just mentioned, works only when the domain of the given vector field is, so to speak, connected. What does that mean? This means this. So suppose our vector field is given like this. X component is x over x squared plus y squared minus 1. And then y component is xy cubed. Okay. And then, first of all, what is the domain? Well, domain of the vector field is a set of all points that can be plugged in without getting any trouble. What do you mean by without getting any trouble? Well, that means without getting 0 on the denominator or negative number for the root, square root, or negative number, a non-positive number for log, or things like that. Okay, without getting any trouble, which xy can be plugged in for this case? Well, in this case, y component, for the y component, you can plug in any xy you like without getting in trouble. But here, you don't want to have 0 on the denominator, so that means you have to exclude xy such that x squared plus y squared negative 1 is 0 from the denominator. That means the domain of this is a set of all xy on the xy plane such that x squared plus y squared minus 1 is not 0. Okay. This cannot be 0. So another way of saying this is not 1. Okay, so that's the domain. And pictorially, this means it's basically everything except on the circle with radius 1. So you have to exclude the circle with radius 1 from the domain. 1, 1, negative 1, negative 1. And everything inside, strictly inside the circle, is in the domain. And everything strictly outside the circle is also in the domain. But all the points on the circle cannot be on the domain. Then now, if you look at this domain, this is not connected. That's what connected means, basically. This is not connected. because it has two separate regions, so to speak. Regions. The region inside the circle and the region outside the circle. So this kind of domain is called not connected, actually disconnected. But in order for the theorem to work, the domain has to be connected. So that means in order to check if this vector field is conservative or not, the above theorem doesn't work actually. So, excuse me. More generally, if you have just a region like this, it's like one island. Okay, this region is called connected. But if you have more than one connected regions, if you combine like two islands, if you have two islands like this, such a region is called not connected. And in order for the theorem to work, we need to make sure that the domain is connected. But it's a little side remark, so it's not super important, but just let me mention it. All right, then finally, as the last thing in this video, let me work out one example of a vector field with three variables, namely to check whether a given vector field f of x, y, z, namely vector field on R3. So therefore, it has three components, P, Q, R. Okay, now to check given the vector field is conservative, let's wait until section 16.5. I'll get to this later. Wait until section. So concept of conservative vector field makes sense even for vector field of three variables, because all you need is just this. If vector field is given as a gradient for f of x, y, z, okay, three variables, we say that f is conservative. Then now, how do you check if it's conservative or not? Well, the theorem here, this theorem is only for vector field on R3, so you have only x, y. But if you have x, y, and z, you need some other theorem. But for that, I'll get to this section 16.5. However, you could do the analogous theorem, analogous actually problem, as this example. Namely, if you know that a vector field is conservative, you can find its antiderivative. So let me just work out one example for this. So let f of x, y, z is y squared 2xy plus e to the power of 3y and 3y e to the power of 3z. I'm sorry, this is 3z. Okay, let me make sure I copy the problem correct. Okay, and then this is conservative. So for the sake of this particular problem, you don't have to show this. This is conservative. And like I said, to check if this is conservative or not is covered in section 16.5. But anyway, it's a conservative, so let's find f of x, y, z so that the vector field is written as the gradient of this f. Namely, this is like antiderivative. Okay, the idea is basically the same as this example, this computation, the computation we did here. But it's slightly longer because we have three variables. And here's the way to do it. Here's the answer. So gradient of f is, by definition, each component is each partial derivative. And we want this to be equal to this. Y squared 2xy plus e to the power of 3z, and then 3y e to the power of 3z. Okay, so therefore from this, f sub x has to be equal to y squared, and f sub y is equal to this, y squared, sorry, 2xy plus e to the power of 3z, and f sub z, the third component, is this, 3y e to the power of 3z. Okay, and then by using those three, first of all, from the first one, in order to recover little f, what you have to do is to integrate little f, namely in this case y squared, integrate little f of f sub y with y, which is y squared with let me repeat again. So in order to recover f from this, what you have to do is to integrate y squared with the variable x. So that means y squared is treated as a constant, so y squared x plus, well, don't forget to add c, the constant of integration. But for this procedure, you are considering y and z as constants. So that means y and z are treated like constants. So that means constant of integration is actually a function of y and z. Okay, then now from this, let's differentiate with y. Then you get 2yx plus. Now you differentiate this with y. Okay, then this has to be equal to this. This has to be equal to 2xy plus e to the power of 3z. So here is the same as here. Then now you'll see that if you look at this equality, 2xy get cancelled out, and then from this, z. Okay, then now here we want to recover g, but g is a function of y and z, and if you differentiate it with y, you get this. So that means in order to recover g, what you have to do is to integrate this with y. So that means you get y e to the power of 3z, and then don't forget to add the constant of integration. But what's the constant of integration in this case? Well, here for this procedure, we are viewing z as a constant. So that means what you're left with is a function of z, so h of z, for some h of z. Okay, so therefore, what do we have? Well, f or f of xy is this plus this, y squared x plus g, but g is y e to the power of 3z plus h of z. Okay, then now we're gonna use the last one finally. You differentiate this with z, you get, what do you get? You get 0 here and here. A 3y e to the power of 3z plus, now this is just the regular derivative of h with respect to z, and that is equal to z. Okay, and then if you look at this portion, okay, so here this comes from here. And then if you look at this portion, this and this get cancelled out. And then what you're left with is h prime of z is just a 0. 0. So in order to recover h, what you have to do is integrate 0 with z. That's just a constant. Literally the constant, just a number. Constant. Okay, so therefore, the final answer is f of x y z is y squared x plus y e to the power of 3z plus h of z, but h of z is just a constant. So we have a constant k. So that's the answer. Okay, so in this way, even in the case of f of x, y, z function vector field of 3 variables, if you already know that it's conservative, you can find its antiderivative in this way. Okay, so that's all I have to say about this section. So this is the end of the video.